This episode is brought to you by Brilliant. We often imagine a future in which the moon is inhabited, with domes and outposts scattered around its surface, but what does a truly developed and colonized moon look like 1,000 years from now? So today we are returning to one of our favorite places in the universe, our nearest neighboring world, our own moon, to contemplate the idea of a late-stage colony of the moon when it's reached populations as high or higher than the Earth itself currently has. We're going to ask what the moon would be like if it was home to many billions or even trillions, and what pathway might lead to it becoming a single, massive, worldwide megacity, what we call a Ecumenopolis. This is not our first time visiting the moon here on SFIA. I try to get an episode in about the moon and Mars each about once a year or so, and for the moon we began with moon-based concepts back in early 2016, then Industrializing the Moon, Battle for the Moon, Moon Industrial Complex, Moon Crater Cities, Return to the Moon, and then last year, Mars First vs. Moon First. In all those episodes, and as side topics of many others, we have discussed how to get a base on the moon and grow those to be real cities and colonies, and some of the possible long-range fates of our moon, how to make the moon a titan of industry fueling our expansion into space, how to terraform the moon so it's green and blue in spite of its low gravity, and even how to raise that gravity by putting an artificial small black hole in its center. And we're going to begin by discussing those last two options in conjunction before moving on to look at making the entire moon one vast, three-dimensional sphere of a city. However, when it comes to those last two, terraforming the moon and altering its gravity, it ignores the development of communities there and the problems of terraforming a built-up and colonized moon, and it ignores that raising the gravity on the moon would alter its geology. Terraforming an inhabited world is just not the same as a dead one. The internal meat and bones of a world are based around a certain gravity. Multiplying it sixfold to Earth normal gravity would be ruinous to everything there, including buildings we previously made. That can be managed, but it's a pretty big hurdle, especially given the structures and locations most sensitive to a change in gravity would probably be all the old historical early buildings we made there, as well as any early domed ecosystems whose organisms had the most time to adapt to low gravity. What's more, terraforming a planet is inherently destructive to the existing landscape. As an example, everything we call a mountain on the moon is really a giant crater rim wall, or a portion of one. They are tall and sharp and would never last on Earth, where gravity and air and water would bring them down in short order. On the moon, those ideal first bases are expected to be in the bottoms of those craters, and we would expect those to be the foci of further colonization, hence why we did an episode called Crater Cities. But if I terraform the moon, then those deep craters valued for the ice we suspect is at their bottoms now become lakes and seas, right over top of the original cities. Now they could persist underwater as domed cities, but that rather defeats the purpose of terraforming the moon so they can get rid of their domes. The moon can never really keep air and water we put on its surface without constant and major replenishment. The gravity is high enough that random room temperature air or water molecules won't go anywhere. The escape velocity of the moon is around 5 times higher than the speed the air molecules would be moving at, but even Earth leaks with an escape velocity almost 5 times higher than the moon's, and that leakage rate would scale exponentially as you drop the mass. So you either have to dome it all over, which is certainly an option, or you raise that gravity and just buttress the world, or you pay a constant replenishment cost of running megafreighters of nitrogen in. So raised gravity seems the best of the three options. We have a few problems though, the first and most obvious of which is that we don't know how to make artificial small black holes. We just have some guesses to how it might be accomplished. I would also guess that as fast as the moon might leak air, even without a protective magnetosphere, which we could add, that it would still be small compared to the amount of mass needed to raise the gravity. Assuming we can make small black holes, then one big advantage that planets that utilize them have over normal planets is that they can be made of super abundant materials like hydrogen, helium, or potentially even dark matter, meaning that you don't have to use up all your rarer building materials like iron and carbon and nitrogen and silicon on generating gravity. Indeed, the main value of hydrogen and helium, which make up virtually all the normal matter in space, is to make energy out of them or to make heavier elements via fusion. As we discussed before, black holes are vastly better and more efficient power generators than fusion, and indeed better at nuclear transmutation of elements too. So you can stick a small black hole in the center of the world in a hollowed out chamber, buttressed via active support, and slowly grow a black hole by dumping hydrogen and helium into it, and use that generated power to run your world. Now, to make the moon have Earth-like gravity on its surface doesn't require as much mass as the Earth has. The moon masses only 1.2% what Earth does, but has 7.4% of the total surface area, and when you're aiming for gravity equal to Earth on some sphere-shaped object, the total mass something needs to have Earth gravity is directly proportional to its surface area. 1/10 the area, 1/10 the mass of Earth. 100 times the area, 100 times the mass, like Saturn, whose surface gravity is very close to Earth's, and which has about 100 times the surface area and mass of Earth. This technique works on any world, be it some tiny asteroid a few kilometers across, or some sprawling mega-Earth a few million kilometers across. See our episode Mega Earths for more details on the building and engineering of such worlds. So the moon masses 1.2% of Earth and would need 7.4% of Earth's mass to have Earth-like surface gravity. This means we need to add 6.2% of Earth's mass to the moon via such a black hole, or 5 times its current mass, which makes it rather debatable which is being added to which, given the black hole would be more massive. Not bigger though, such a black hole would be 1 millimeter wide, which is actually very large for an artificial micro black hole and makes feeding at regular matter so much easier. Now, less gravity would probably be fine for people. Mars gravity might work fine, and if you're curious, this black hole trick would work fine on Mars too, but has the same problem for terraforming there. The moon's surface gravity would now be 100% of Earth's, but its escape velocity from the surface would still be lower, 5.8 kilometers per second, more than twice its current value but still only half of Earth's, and about 20% higher than the escape velocity of Mars. Mars has no real atmosphere or oceans, but we expect it might have in the past, and the gravity was enough to keep them for long times but not for 4 billion years, so the extra 20% might be enough, or it might just slow the escape down to a billion-year timeline, which is good enough for terraforming. Nothing lasts forever, be it a planet or a megastructure or a hybrid of the two. You need to replace and repair. You could go bigger too, expanding the moon to be a hollow shell of Earth's size and mass, making Earth a genuine double planet, and we will come back to that later in the episode. Now, the other problem is that black holes are great power generators. You can add mass straight into one in a way that wouldn't cause power release, but if you are generating power while adding mass, you are getting somewhere between 20 to 40% of the mass energy of that matter released as energy. So you're potentially talking about releasing something like the current entire mass energy of the moon in the process of feeding up to Earth gravity. You're not exactly being wasteful by skipping power generation either. All that energy is not free. If you convert 20% to energy on the drop into the black hole, then you need 20% more mass to get that final desired mass. Whereas, as we'll see in a moment, even slowly adding in that last 1% of mass over a billion years would easily power the moon that entire time. See, a moon mass of energy is 6.5 times 10 to the 39th joules, which is 500,000 years of solar output, or the amount of sunlight that falls on Earth alone in a quadrillion years, or the moon in 14 quadrillion years. And that sunlight is what keeps Earth and the moon warm. So even just adding that mass energy in at the same rate the sun gives it to those worlds would mean roasting the foes on it by doubling their power input, and would take 14 quadrillion years, fully 1,000,000 times longer than the universe currently exists. Now, we might be building for those kind of timescales. Black hole-powered civilizations regard the normal starlit era of the universe that will persist for the next 100 trillion years as that irritating early period of the universe where big clumps of useful fuel were inefficiently burning away their value of their own accord and exploding when they were done. 100 trillion years is nothing to their timescales, and they have the energy efficiency to outlast all the stars in the universe 1,000,000,000,000 times over again. Nonetheless, it's a long time for us to wait, and so you would presumably be adding that mass in a lot faster to a black hole in the center of the moon or some other planet. And I suspect trying to get it in there and quickly is not going to be a clean process with no energy produced, so this trick is likely to need to be a slow one. Or you can make it far away and move it there, but that has its own very tricky issues, since you cannot magically turn off its gravity or inertia when they're inconvenient. Probably anyway. For all we know, we might find some gravity or inertia manipulating technologies, and if they are possible, then I think they're likely to be discovered before the moon is home to billions of people. I'm not optimistic on such technologies, but regard them as vastly more likely than FTL or time travel. Once you're at a good mass though, you can keep adding mass at the rate you want for its energy and using it to power your civilization. Just the last % of a % of the desired mass would power you for trillions of years. And so this is one path to a future moon, one in which it has had its mass raised and had its oceans and atmospheres added to it. Earth is not unaffected by the moon gaining 5 times its current mass, but that is manageable, and you could be using a little of that mass and energy to push the moon a bit further from Earth to keep the tides on Earth of similar intensity. Or you could build sister moons into a Kepler rosette around the moon, or rebuild the whole moon as a big donut around Earth. You could also increase Earth's own mass, as we looked at in our culminating episode of the Earth 2.0 series, Matryoshka Worlds, where we envisioned an Earth with layer after layer of hollow spherical shells, each artificially lit, and full of land and sea, sharing the same mass for gravity on many surfaces, which is another possible fate of the moon as such a Matryoshka world, and indeed given you would be adding so much mass to the moon to do all this, a Matryoshka layer of nested spherical worlds would seem more likely than a single shell, especially as while the moon is low in mass compared to Earth, it's made of mostly the same stuff as Earth's surface. This is the major reason why we think the moon was formed by an ancient collision, tearing much of the Earth's surface off. The Earth might be 80 times the mass of the moon, but the Earth's crust is only about 1% of Earth, so you could turn the moon into an Earth crust thick shell as big as Earth's crust and still have mass to spare, and of course you can make thinner layers given that you don't need a crust that thick. You just disassemble the moon and rebuild it as a shell around a black hole of Earth's mass. The nested shell Matryoshka version might be more popular though, given that the moon's month-long day and night already require artificial lighting, hence underground or lower layer habitation is probably easier to sell to people. Of course, the moon could also be spun up to a 24-hour day, but the energies involved in that are also pretty enormous. And this is another fate for our moon, disassembly, possibly for some world building, possibly to build a fleet of 1 trillion colonization vessels to sail out and claim the galaxy, possibly to build a swarm of O'Neill cylinders and other space habitats and infrastructure around Earth, which is easier without the moon swinging around gravitationally perturbing everything, hence why other artificial moons or a donut moon around Earth might be popular. Now, we did not raise all those other scenarios strictly as alternatives to our moon slowly turning into one vast city or Eucumenopolis, but rather, many are roads we might follow at the same time. For instance, every city needs its parks as well as its ports, and it is possible a lot of moon habitation industry will be underground for safety, but that early domes on the moon would be about landing ships or having gardens, where losing one to be a cracked dome represents less of a loss and risk compared to a home or school or office, and such a habit might persist into a future that sees the moon terraformed on its surface, but principally inhabited below. The key notion whenever we discuss domes on airless worlds, incidentally, is that while one meteor slamming in at kilometers per second could blow a dome to pieces and kill everyone inside, those would be rare and easier to detect and destroy with point defenses, and be vastly outnumbered by the smaller rocks and pebbles, wearing or cracking a dome or blowing a dime-sized hole in one. Air leaks into the vacuum space at roughly the speed of sound, so a dome the size of a football field with even a fist-sized hole in it to the vacuum is not causing everyone to collapse suffocating or get sucked through the hole and turned into a sausage on the way out. Plus, such domes probably have thin wire mesh in their panes or a layer of plastic like with shatterproof windows, not some big sheet of glass that would shatter. Nonetheless, it would seem unlikely many folks would feel comfortable living and sleeping directly under a big dome without additional layers, like being underground would offer. And again, there's no 24-hour day there. It gets dark for 2 weeks in a row and sunny for 2 weeks. Maybe not something folks want to live under. It's hard to guess, but at the very least, early on we would expect a lot of moon colonization to be buried in the sides of craters, or under them, or in the vast lava tubes underground, and artificially lit. From this, especially with Earth probably growing its cities ever more vertical, and other space habitats being essentially rings or cylinders you live inside, we might assume an underground growth on the moon and downwards would be popular from the outset. Skyscrapers are much easier to build on the moon due to the low gravity, lack of air, and lack of earthquakes, but they are exposed to being hit too. Truth be told, a skyscraper, especially something in the arcology megascraper zone, are vastly more resistant to meteor strikes than a big dome is, and more so if you have a bunch of these scrapers under a dome, but still connected via their own protected or airtight tunnels. You have a lot of redundant protection for folks on the surface living in them. You can also have some clever features, like a cannon that shot airbags at cracks in the dome if the dome punctured, or that shot at folks exposed to the vacuum and encapsuled them in an air bubble and protective sheath. Those people also might be effectively immune to being spaced into a vacuum due to being covered in smart matter like we'll discuss next week, or being rather transhuman and cybernetic. We have looked at all sorts of other safety features spaceships, space habitats, and dome colonies might employ down the years too, so I don't want to give the impression that surface living on the moon and surface cities are not viable unless the place has been terraformed and with a black hole crammed in the middle. Still, while building up is easy, so is building down. Excavating on the moon is easy. The regolith is nasty stuff full of sharp edges that are rough on equipment, but the gravity is lower, which makes everything else about excavating and building down easier. For that matter, Stanford developed an interesting vine-like growing machinery that might get around the whole regolith cutting and ripping issue. Keep in mind, we have lava tubes on the moon in which you could fit football fields, and which can be many kilometers long too. And it's not that the moon forms those better than Earth, it's that lava tubes, especially big ones, have more problems lasting on Earth with earthquakes and water and air and gravity. Digging down and building up are easier on the moon. But the difference is that when you're digging down, you are surrounded by tons of rock that's fairly airtight in its own right and easily covered with a sealant to minimize small leakage. On the surface, building up, you either build under a big pressurized tent or you build then pressurize, and unless you built very thick, meters not centimeters, odds are good you'd be springing leaks as you pressurized that building or found them when the tent around it was removed. Now that low gravity lets you not only build taller or deeper more easily on Earth, but also lets you contemplate heights and depths you never could on Earth. There is no end of atmosphere on the moon, it's got none, so all the buildings need to be pressurized anyway, and they're not getting hammered by wind and storms, or earthquakes. There is much less of an infernally hot mantle below, which makes building deeper easier because there is much more crust than on Earth. We do believe the moon has a liquid iron outer core and mantle, but far smaller and deeper down. Of course, running into magma and lava monsters is not the real limit on building deep on Earth. We max out much shallower. We usually put the limit on cave depth at about 2 miles or 3 kilometers underground because of the pressure of overlying rock, and we do have some mines as much as 4 kilometers deep, but these are almost exclusively gold mines, because tracing a vein of gold that deep is about the only thing worth the effort of trying to excavate, shore up, and maintain such a tunnel for. Something to keep in mind is that even your air is getting compressed down there by air above, and can be twice the pressure of that up here on the surface, and has to be pumped down refrigerated into an insulated shaft to make it a bearable temperature for the miners. Now, robots may do better one day, but that doesn't interest us much for living accommodations. But since gravity on the moon is a sixth of Earth's, we could go 6 times deeper before the air rose to that pressure. What's more, there is no air on the moon, so it's not leaking down through various cracks to raise that air pressure. If I take a big jug of water, the pressure at its bottom is higher than at its top. If I place another jug on top of it, that jug presses down to raise the pressure further. However, if I instead sit them on a shelf, one below and one on the shelf above, then the one above does nothing to add to the pressure. With that in mind, on the moon you can circumvent that pressure issue by just having airlocks, which you would have anyway, separating levels every so often, maybe every kilometer at most. And thus your pressure need not rise as you go deeper, and even at its core the moon is only thought to be about 1300 to 1400 Celsius, or around 2500 Fahrenheit, whereas Earth's core is about 5200 Celsius or 9300 Fahrenheit. nearly as hot as the photosphere surface of the sun. And that means you can build very deep on the moon. Indeed, we do have metals able to withstand that core temperature, many of them. The pressure might be harder though, especially in conjunction with temperature, as its core pressure is about 45,000 atmospheres, which is nothing compared to Earth's core, which is 80 times higher at 3.6 million atmospheres, but that's still about 10 times the pressure at the bottom of the Kola super borehole that got 12 kilometers deep. Still, it's inside the realm of what we can plausibly do, even without some of the more extreme methods we looked at in our episode Accessing the Earth's Core, which means even a tunnel right through the middle of the moon is viable. For those who've seen the movie Total Recall, the reboot rather than the original, you might recall they had a train shaft that went right through the center of the Earth between Europe and Australia. There's not much reason to do such a project on Earth, but it works much better on the moon. You just drop down a shaft and you will accelerate as you fall, especially if it's already a vacuum, and gravity gradually decreases as you fall until it drops to nothing at the core, then reverses. So the same gravity that sped you up slows you down on the way back up to the other side of the tunnel, which theoretically makes this manner of travel cost you no energy at all, though in practice you probably need a little to overcome friction on the train system. Now on Earth that means a journey of just 40 minutes and a maximum velocity of 8 kilometers per second, which is roughly the same as low orbital speed right over our atmosphere, and that is not a coincidence since both have to do with falling around the planet. Orbital speed right over the moon's surface is 1.6 kilometers per second, and that's the maximum speed you'd reach falling through a shaft bored right through the moon, all the way down to the center and back out again. The time it takes to fall, assuming a sphere of uniform density, is pi times the square root of the sphere's radius divided by the gravity at the surface, and is a formula that dates all the way back to Sir Isaac Newton and his original work on gravity, physics, and calculus. Needless to say, worlds are rarely of uniform density, but it tends to give a decent approximation, and for the moon, with a radius of 1.7 million meters and a surface gravity of 1.6 meters per second squared, that gives us a time of 3,250 seconds, or 54 minutes. Weird that it takes longer than on Earth, right? Well, not really. The moon isn't as dense as Earth. The denser the sphere, the faster you fall through it, something that is pretty handy if you're trying to build black hole wormhole gates. For the same reason a satellite right over the moon actually takes longer to orbit it than one right over Earth does, for all that Earth is much bigger. If you're curious, it's 42 minutes on Mercury too, which has about the same density as Earth, even though it's about a 20th of our mass, just over a third of our diameter, and has only 38% of our gravity. Your fall time, or orbit time, as it's basically just half an ultra-elliptical orbital path, rises with the square root of radius, but surface gravity of a uniform sphere is dropping with the square of radius from gravity weakening with distance, and rising with the cube of radius as it encompasses a bigger volume and thus more mass, so that surface gravity of a uniform dense sphere rises with the radius, double the radius, double the surface gravity. Thus your orbital period or drop times are rising with the square root of radius divided by the radius, or it washes out. A big sphere of Earth's density but way bigger radius has the same drop time, hence density is altering gravity linearly, twice the density, twice the mass in a given sphere, twice the gravity, but it's still under that square root, so drop time follows with the inverse square root of density, 40 minutes for Earth, about half that for something 4 times denser, and twice that for something a fourth as dense, which would generally be your icy moons or dwarf planets like Pluto. A little bit of physics and gravity sidetrack there, but the show is called Science and Futurism, and I am a physicist, so I like to sneak some in when I can. Don't worry, there's no quiz. In any event, these kind of tunnels don't actually have to bore all the way through the core. They can run at tangents through a planet like if you jammed a needle through an orange, in one place and out the other, regardless if it passes through the core. The problem is, on Earth, that orange peel is still proportionally thicker than our crust, so these sorts of gravity trains are not really practical on Earth. You're not really getting up to that bullet speed for trains, running at a maximum depth of maybe 4 kilometers, requiring hyper-strong vacuum tunnels. In truth, it wouldn't be a needle straight distance either. Your shortest time tunnel in a case like this is a hypocycloid, a curve rather than a straight line, and allows us to contemplate, on a place like the moon, gravity-trained tunnels all over that world that move you around it very quickly, right from the bottom of one crater city to another, far away. Now, why does this matter? Well, my thinking is that if you're building crater cities and connecting each to each other by such hypocycloid tunnels for quick, easy, and safe travel, then much like any highway with exit ramps or train path, you might have buildups near and on these, especially if it's not hard to stop the train partway through and store some drop energy. It's not like interstellar travel through a vacuum where stopping and starting partway through the journey costs you as much as the original journey. This costs you no energy, and since you're presumably dropping down an electromagnet-covered shaft, there's a number of options for low or no energy turns and stops, including utilizing a simple flywheel, which work great in a vacuum. These are your safest paths too, including launching up into space and back down again, except for some of the extreme and fuel-crazy options we contemplate in our high-tech search and rescue episode. We're also talking maximum speeds of about a kilometer a second here after a drop of 10 minutes, as that would already put you 300 kilometers down under the surface. Deeper journeys could get you all the way up to that 1.6 kilometers per second orbital or core speed, but even at 100 kilometers deep, you've already hit 353 meters per second, just over the speed of sound here on Earth, and truth be told, it doesn't take much energy to stop or start in a vacuum with something to grab on and shove off of. A 1-ton car going at that speed has a kinetic energy of just over 60 million joules, half a gallon of gasoline, so we're not talking a ton of energy to stop for a pause and get back going even if the system doesn't include regenerative braking options and such. This means all along those big hypocycloids between the bigger crater cities, or lava tube cities for that matter, you will likely have a lot of pit stops like you do on highways. This decade's pit stop becomes next decade's truck stop, and then a town, and then maybe a city in its own right. So we could easily see a big expansion all over the surface of the moon, like we discussed in Battle for the Moon, while at the same time we had an ever-growing number of these tunnels and the growing habitation around them. All the more so because these are great places to put a long, skinny rotating cylinder to serve as rotating gravity spots so that residents or visitors could experience gravity closer to terrestrial standards. One other thing driving this expansion is that folks live on the moon for a reason, and the big reason would seem to be mining raw materials, and such hypocycloids represent very low energy ways to launch spaceships too. They are very easily modified to serve as a mass driver or space catapult. It would not be surprising to see mining following along these paths to get a dual use as basically creating a highway or freight line while producing the valuable ores that will be feedstock of a lunar economy. Now, speaking of localized gravity, I suppose it's only fair to point out that a single big black hole isn't the only option for gravity on the moon. If you're good with your black hole generation, you could have dozens of smaller ones forming your grid beneath the city on the surface, giving it higher gravity locally. You can do the same trick on high gravity worlds to lower gravity in a city by suspending them above it, and absolutely works on paper, but has always struck me as way more dangerous than a single big one at your planet core or moon core. They could be used for power generation as needed, and indeed if they are small and numerous enough, they could generate power via Hawking radiation. When able to provide Earth-like gravity 100 meters away, generates a few hundred watts that way, and you could potentially make a floor of them in some hexagonal grid layout every dozen meters or so that might give you a nice plane of gravity and power generation. This is one trick for artificial gravity plating like we see in science fiction, and generally gravity will not drop much as you get higher from those plates until you are as high or higher than the plates are wide as a whole. Look up calculating the gravity of an infinite flat plane if you want that explained. We've already done a bit more math today than I prefer our episodes contain. So as long as your city is at least as wide as it is tall, you can use a giant plate full of micro black holes for gravity generation. Note that on the surface of the moon, this would mean you would have an upside down under city where the gravity was 67% of Earth normal, but pointed upwards and outwards, not down, since your plate is presumably generating less than Earth gravity, as the moon provides some too, and it's subtracting it instead of adding it when upside down. So there are potentially some weird tricks for making coin-like cities with heads and tails, on or off planets, or hanging over top one too. Alright, one other note on gravity before we move to why the moon might become a megacity. Expansion of a planet by digging down and hollowing out and using that material to build higher levels lowers pressure and gravity as you hollow it out and make it wider. That makes your gravity drop tunnels slower by a bit, as you make your world bigger and less dense. Note that having all your gravity at the core in a black hole makes the drop faster than a uniform sphere of that same mass too. However, as folks core out the moon to make more living space and mine it all, it is likely a lot of that spoil will be moved up to the surface for construction, and on long timelines and with vast industrial might, this starts getting you the mini-layered Eucumenopolis or even Matryoshka world setup we sometimes contemplate as Earth's eventual fate. So we build down in craters and lava tubes, deep into their rim walls too, and slowly as population rises, we build deeper and wider and merge, all at the same time you're piling on new layers above, making the whole world structure more artificial and sturdy, and potentially bringing in cheap mass from elsewhere, be it liquid hydrogen or helium or black holes, to add mass if you want to. How many people could comfortably fit in the moon if we made it a three-dimensional city? A tricky question, as we always have the fuel, food, and heat issues, not to mention as you hollow it out to make homes, that excess material can be used to make more homes on higher levels. Its current volume is 22 times 10 to the 18th cubic meters, or 22 billion, and the typical apartment might be as little as 220 cubic meters, and hardly uncomfortably tiny at that, so you could squeeze in 100 million billion people, a number that even a Dyson swarm would find respectable, but in truth more the sort of number we would expect as the upper end for an entire cis-lunar or Earth-Hillsphere planet swarm. See our episode on colonizing cis-lunar space for more explanation of that. We're not really contemplating packing people into endless apartments on the moon anyway, but would probably instead use a figure more like 10 trillion, as it represents the high upper end of what the moon could get rid of as heat, even if rather expanded in radius, from many layers of radiating super towers being added, while still giving us people on the order of 10 kilowatts apiece for comfort, hydroponic food production, commerce, etc. You could go higher in energy needs for fewer people, or lower maybe, especially if people are getting pretty post-human like cyborgs or digital uploads, but let's settle to 10 trillion. If we optimistically assume 10% of the human population lived on the moon at that point, and the human population grew like it did in the 20th century or the last 20 years, doubling twice a century, then that human population of 100 trillion might be reached in as little as 8 or 9 centuries, near the dawn of the 4th millennium. And personally, I would have a hard time imagining a terraforming project that might take many more millennia to make the moon blue and green would be allowed to override those efforts and expansions, so that at most, the world's surface might look that way, covered in golden domes, super spiral buildings, and spaceports, while the juggernaut lay below. Now, it's popular in science fiction to portray Mars as some giant empire breakaway from Earth, like the US is often seen as being for Europe, or even as dual empires of roughly equal footing such as we see in The Expanse or the Warhammer 40,000 settings. And usually, if the moon is mentioned at all, it's as a footnote, or perhaps properly, as a small satellite power, but in truth the moon's role in the future is likely to be bigger and brighter than Mars. If any world is likely to ever rival Earth or even come near it, it will be our own moon, not Venus or Mars or some world around Alpha Centauri. It may make itself mighty by slowly extracting matter to build itself and its economy, fueling the push to develop a vast solar empire and a vast collection of industry and habitats in cislunar space, all while importing cheap matter such as hydrogen or helium to increase itself in mass. Here though we see an option where the moon might rise to be a true double planet to Earth, its twin and peer, as we settle the solar system and galaxy beyond. So we have a few announcements and our upcoming schedule for April to get to, but first, we were doing some math today to calculate how big a black hole needed to be to emulate Earth-like gravity on the moon, and we do try to keep how much math we do during an episode on the light side. Watching science videos like ours is a great way to get an overview and learn the basics of different topics. But to gain an understanding of why and how concepts work the way they do, you have to try it yourself, And for that, I recommend heading over to Brilliant, today's sponsor. Brilliant is an interactive STEM learning platform that helps you truly understand concepts in math, science, and computer science by guiding you through engaging hands-on courses. Now, a lot of folks who watch the show love our topics, but think of themselves as bad at math, and they'd love to know more, but they don't think they can. Many of us learned there was only one right way to approach things like math, but in Brilliant's new Everyday Math course, that's not the case. Exercises like finding the area of shapes will show you there are many ways to solve a problem, and the visual and interactive solutions will help you understand the concepts even better. And don't worry if you're busy, lessons are presented in bite-sized pieces, so you can learn at your own pace in a no-pressure environment. To get started for free, visit brilliant.org/IsaacArthur or click on the link in the description, and the first 200 of you will get 20% off Brilliant's annual premium subscription. So this is the first episode I've produced since I got back from my trip to Santa Monica to speak at the RAND Corporation's US-Japan Space Cooperation Conference about 2 weeks before this airs. The conference was a lot of fun, and dinner at the Japanese consulate afterwards was spectacular in cuisine, conversation, and courtesy. I think I came up with a dozen different episode ideas while listening and chatting with others, particularly Pete Warden from Breakthrough Starshot. The man's a legend and he deserves the status. The opening keynote on day one was David Kipping, who a lot of you know from the Cool Words Lab and channel, and we ended up chatting for a couple hours afterward while boarding time for our flights home. And for everyone who's watched his channel, yes, he is every bit as insightful and pleasant to talk to as you would expect. If you haven't seen his show, and especially if you're a Fermi Paradox fan, check out his episode The First Civilization to Emerge in the Galaxy. His narrative on that episode is spellbinding, and don't forget to hit the like and subscribe button while you're there. Speaking of fellow science creators, and on a sadder note, I also wanted to express the condolences of myself and the SFIA team to Anton Petrov on the recent loss of his baby boy, Neil Apollo Petrov. I cannot imagine anything worse than that, and since I know we share a lot of audience, I would just ask everyone to continue to give him your kind words and support during this hard time. It has been a rough couple months for many folks on the back of what seems to be just a brutal last couple years of virus-driven, emotionally grinding change and hardship, and I try not to sugarcoat how hard times can be on this show, even though we aim for an optimistic tone, and I do believe in a brighter future if we work hard for it. Stormy weather brings the rain that makes the flowers grow, and there is a light at the end of the tunnel. Admittedly, sometimes it feels like the light at the end of the tunnel is actually a freight train getting ready to run you over. I have a feeling that this is going to continue to be one of those kind of years, and it's important to stay strong, keep to your courage and convictions, and just keep working to a better world, and not to let events weigh you down so much you forget to see the good moments along the trip too. There is a lot of future to look forward to as well, and we had best get to it by finishing up our schedule of episodes so we can finish up this episode. We are almost finished with March 2, and we'll close out this weekend with our live stream Q&A, followed by a look at programmable and smart matter on March 31st. Then we'll open up April with a look at the concept of self-growing space habitats and bases. After that we have our Sci-Fi Sunday episode, Multi-Species Empires, followed by asking what would happen if Earth lost the Sun and became a rogue planet. Now if you want alerts when those and other episodes come out, make sure to subscribe to the channel and hit the notifications bell. And if you enjoyed this episode, please hit the like button and share it with others, and leave a comment below. You can also join the conversation on any of our social media forums, find our audio-only versions of the show, or donate to support future episodes, and all those options and more are listed in links in the episode description. Until next time, thanks for watching, and have a great week.